Hey Algebra 1. So today we're going to go over really quick the extensions, and then we are also going to see how we are going to solve some real life problems with quadratics using some technology. So our extension activities after Friday are going to be about solving the problems longhand using mathematics, because we won't always have access to the graphing calculators and whatnot, and so we're going to look at that after or during the next couple of weeks. Okay, so the first thing we want to look at is the extensions here. So this first question was about how tall is the shooter? Well, he is about 6 feet, maybe 6'2", maybe. But somewhere around 6 feet is what we were looking for. And that right there is our y-intercept. That's the initial value of the parabola. You can see how his head lines up there with the basketball in this arc. So that's the initial value. And when we're looking at the initial value, let me get my, oh, hang on, let me pause this. Okay, here we go. So this is the poster that I usually have hanging up in my room. And we can see that the y-intercept in the form ax squared plus bx plus c, or I guess y equals ax squared plus bx plus c, because, that's the graphing version. You put a y and x's. This y-intercept is the c term in the equation. Okay, so that is really helpful whenever we are going to be dealing with the word problems here shortly. Okay, so that was this one. His initial value is that height of the shooter. Then this question says, what does it say that the coordinates of the basketball hoop are? And so this was about 1910, because remember, it goes x first and then y. And so that means that it is 19 feet away from the shooter and 10 feet tall. And so a specific point has a lot to say if you know what the x and y axes represent. This is feet away from the shooter. This is feet in the air. Now we are going to see that not every quadratic is mapping a trajectory, and so that's going to be very important. Okay, last one. This is a special equation format that you'll talk about in Algebra 2. This is called vertex form. And it says that the equation references this coordinate. And what is that coordinate? Well, if we look at it, this is like almost 11 and almost 15. And so that's the vertex. That is the highest altitude at this specific distance away from the shooter that the ball will get. So that is the vertex. And so again, that is seen right here. And there is also a formula for the vertex, and that is negative b over 2a. And so that is where you can find the x value of the vertex, and then you plug it back into the original formula, and then you get your y coordinate out. And so this will actually give you the axis of symmetry, and then you plug it back into that. Anyway, you'll see that a lot more in Algebra 2. Really, this year, I just want to make sure that you've got the basics. We found out how to do the zeros just by solving the equations when it hits the ground, whatever. Okay, so that is the long and the short of that. So the next thing I want to do is show you some word problems here. And we'll do this one in a moment because I want to have a graphic with this. I'm going to show you how to use the Desmos calculator. But the first question that I want to look at is this one. The following graph shows the height of a pumpkin chucked out of a catapult after t seconds. Here's the deal. This is not how far away the pumpkin is going to land. This is not how far away from the catapult this is away. This is a matter of time. And so think about if you're on a trampoline and actually, hang on, let me find a video of that. Okay, here's a quick snippet. So notice whenever she reaches the apex of her bounce, she kind of slows down. And that's what I'm talking about as far as height compared to time. And so that is what is modeled with a quadratic formula, is her height compared to the time. And so see how whenever she reaches her highest point, there's a little bit of hang time, and that's like that zero gravity moment if you've ever been on a trampoline, which I'm sure you have. So let's look again there, and she's there. Okay, so that is what we're modeling with this particular problem, is that the pumpkin is going to be chunked up, and then it's going to have that small 0G hang time, and then it's going to come back down. Is it going to travel in an arc? Yeah, most likely. But this does not show the travel of the pumpkin. This shows its height. And so that is a key distinction that we need to make. All right, so what was the height of the pumpkin whenever it was released? Well, that's the initial value. And so it was 16 feet. Yeah, 16 feet. And so what that means is that the trebuchet or the catapult or whatever it is, its arm releases the pumpkin at a height of 16 feet. And so it's got a pretty big arm on there. What's the maximum height that the pumpkin achieved? And so this is the height in feet. And so it was 25. So it got 25 feet up in the air. And how long did it take for it to reach that maximum height? And so that's where we're looking at how long. This is the time in seconds. And so it looks like 3, because I can count. So it should have taken 3 seconds to reach its maximum height. This one, what is the height of the pumpkin at 1 second? So after 1 second, how high was it? And so that is the X value 1, Y value, I'd say about 21. So it was 21 feet in the air after 1 second. How long was the pumpkin airborne? And so that's when we need to kind of interpret this a little bit more, is when did it hit the ground? And in order to hit the ground, that means that the height of the pumpkin would be 0. And so after how many seconds was the height of the pumpkin 0? And if I counted right, that looks like 8 seconds. So after 8 seconds, the pumpkin is going to crash down. Now, what does the 0.79 represent? Now remember, this is our X value, this is our Y value. So this is time. After 7 seconds, and the Y value represents height, it was 9 feet in the air. I don't have to look over here because, if this is the point, then 7, 9, it's right there. But just interpreting it based on what the X and Y value represent. So after 7 seconds, the height or the altitude or whatever of the pumpkin is 9 feet. After 7 seconds, the pumpkin is 9 feet off the ground. So after 7 seconds, you're still not going to have anybody, at risk of getting conked in the head with a pumpkin. That would be a little bit more around here. About 7.5 seconds is when it hits that 6-foot mark, and that's whenever it starts really getting dangerous. Okay, So here we had this graph already pre-made for us. We did not have an equation. This was all just in picture form. And so that's what we're going to do today. I'm going to show you how to get one of these pictures, and then we're going to interpret it. Your 4 problems are going to be over here. This again is height versus time. This is not trajectory. This is just like the bouncy person on the trampoline or the pumpkin. This is all about its height relative to time. And let's see, the rocket's height is given as far as time is concerned. It didn't say time, but t here represents time, and so we should write that. Alrighty. Okay. And then here we go. A stuntman leaps off a tall building. The distance in feet is given by this in the ground t seconds after he jumps. Okay. So again, we see these. All of these -16 or -4.9, that is all having to do with the gravitational pull of the Earth. And it's really neat. And you'll get to that in physics. And then here's the last one. This is a dive limited by this equation, where y is your depth and x is the time in seconds. And so this is also a really neat one. But again, it's all just interpreting the graph. So we are going to split the screen here. There we go. And so this is the Desmos graphing calculator. And what I did to go here, not just calculator because it may take you to the scientific one, I just searched Desmos graphing calculator. So I'm going to make this half of my screen again. Okay, so a water balloon is catapulted into the air so that its height in meters after t seconds is represented by this. And what I really need to do is get a graphic for that. So -4.9 t squared plus 27 t plus, that's an equal sign, sorry, plus 2.4. And how I got this to be an exponent is just the same way that I type it in the regular thing over here, is put caret squared, and it automatically takes you up here. So that's cool. All right. Well, that's wrong. Oh, try adding y equals. Okay, so sometimes it wants me to and sometimes it doesn't, but there we go. Alrighty. So first I'm going to make this big again so that I can actually get this where I want it to be. And so I just need to shrink this up a little bit. There we go. Oh dear, shrunk it too much. Alrighty, so we want to see the y-intercept, the x-intercepts, and my mouse is so sensitive, in the vertex. Okay, stop now. There. All right. And so here, those have been highlighted because Desmos knows that those are the most important things on our stuff. And what's neat is that we are given, like if we hover over those points, then we can actually see what they are without having to do any calculations. So that's really neat. This is a super helpful tool. Okay, so how high is the balloon after 1 second? And so at x equals 1, this might be where I need to really blow this up. And so at x equals 1, what is my y value? Well, dang. Okay, there we go. Is this x equals 1? Oh no, that's a half. Wow. Okay, so I zoomed in way too much. Alrighty, there we go. And it should be really, really close to, if not exactly, 25. And you know what we could do is we could actually say x equals 1 and see where these two intersect. So there's that. So how high is the balloon after 1 second? It is 24.5 feet high. What's the maximum height of the balloon? And so going back to this, and there we go. Going back to this one, the maximum height of the balloon, remember the height is given by the y, so the y value on the vertex. After 2.755 seconds, the height will be 39.594. And so, what did I just say? Gosh, 39.594. Okay, so the maximum height will be 39.594 feet. And so if you want to round that to 1 decimal place, 39.6 feet would also be acceptable. Okay. Alrighty. When will the balloon burst as it hits the ground? Okay, so when is this going to hit the ground? After how many seconds will it hit the ground? Well, we have two values of 0 here, and those are negative something. We can't go backwards in time, so this is not applicable to real life. And here at 5.598, so at approximately 5.6 seconds. I do have another question for you, because several of your problems over here talk about initial value. So a water balloon is catapulted into the air. If you think about how you would catapult a water balloon, maybe you're throwing it underhand, and then at the point that you're letting it go, that's its initial value. So at what point was this let go? Or maybe we had a really small catapult, one of those yard catapults that kids play with whenever they're having a water balloon fight. How high was that catapult? Whenever it was initially let go, the balloon was 2.4 feet off the ground. And so that's what this point represents. And you can see that that is right here, which it's not highlighting because it's got a text box tool. All right, so that is pretty much the idea. And this is another 20-minute video. Way to go. All right, sorry guys. So what I want you to do is I want you to use the Desmos calculator, the Desmos graphing calculator, and I want you to take the graph and type it in over here and use the picture to interpret. Sorry. I was sitting on my foot weird. Anyway, so use the picture to interpret and find the answers here. Now, this last one on the soccer ball here, when will the ball's height be 3 meters? That is a Y value thing. And so over here, if I ask you, when is the water balloon going to be 5 meters off the ground, or 5 feet off the ground, whatever this was in, instead of saying x equals 1, I would find the line y equals 1. Y equals 5. There we go. And I would determine when these two lines cross. And so that would cross at not even 1/10 of a second, and over here at 5 and almost 1/2 seconds. And so that's how you would determine as far as height that would be. Okay, so don't know how well I explained this one, but if you have any questions, please reach out and make sure that you have your picture on hand so that if we need to discuss your Desmos graph, then we can. All right, guys, 4 questions for you, and I will talk to you later. Bye-bye.